crystal parameters of hexagonal closed pack structure, that is HCP. In this lesson, you will learn to explain closed packed hexagonal structure, calculate the number of atoms per unit cell of HCP structure, calculate the coordination number of HCP structure, calculate the atomic radius of HCP structure, deduce the relation between C and A or the so-called C by A ratio, calculate the atomic packing factor for HCP structure. Our modern aircraft engineers have always devised several ways to save fuel, and cutting down weight is one of the key approaches used. The engine here plays a major role for the aircraft to take off. As the air gushes into the large turbine blades of engine with a very great velocity, it facilitates thrust and the plane can move forward, thus taking off. So, a lighter blade facilitates the engine to blow more air backward with very high velocity and thus save fuel. The use of titanium alumide in turbine blades has made it less heavy, around 45% in comparison to the traditional nickel alloy that have been used in the past. Titanium in its purest form does not have high strength, but its alloy titanium alumide is a high-strength product with low density. But why is titanium ideal for aeronautic architecture? Titanium is a metal with a hexagonal close packing close to ideal C by A ratio, or in other words, the length to edge parameter is nearly ideal. At a temperature of 890 degrees Celsius, which is called alpha phase, it has a hexagonal close pack structure. However, on heating, the phase changes to beta phase with a body-centered cubic structure. This is a more ductile phase with a greater number of slip systems used widely. Thus, we conclude that manipulation of crystal parameters of HCP structures such as titanium metal is of immense help to us. In this module, let us further explore the hexagonal close packing structure and determine the crystal parameters of a HCP. In a hexagonal close pack structure or HCP structure, there are 3 layers of atoms. In the top layer, we have 6 atoms at the corners of the hexagon with a central atom. Similarly, the bottom layer also has 6 atoms at the corners with a central atom, or totally we say there are 12 atoms placed at the 12 corners of the hexagon. Apart from the corner atoms and base atoms, 3 atoms are positioned within the faces which are not shared by other unit cells. If C is the height of the given unit cell, then the middle layer is at a distance of C by 2 from the bottom layer. Let us now proceed to understand the fundamental quantities to describe this crystal structure. The crystal parameters such as effective number, coordination number, atomic radius, and packing fraction and C by A ratio that describes a crystal. Effective number is the total number of atoms present or shared by a unit cell. In the HCP structure, we have 3 types of atoms, namely corner atoms, base atoms, and middle layer atoms. Observe the corner atom here. Do you find that it is surrounded by 6 atoms? Let us now slice off the corner atoms to observe their contribution to this unit cell. That means each corner atom contributes 1/6 of itself to the unit cell, and the number of atoms per unit cell is equal to 1 by 6 into 12, which is equal to 2. How about the base-centered atoms? Each base atom will be shared by 2 unit cells, and the number of base-centered atoms per unit cell is equal to 1 by 2 into 2, which is equal to 1. In the case of middle layer, there are 3 middle atoms per unit cell, which are shared only by that unit cell, and the number of middle layer atoms per unit cell is also 3. Therefore, the total number of atoms per unit cell is equal to 6. We have learnt that coordination number is the number of neighboring atoms in a unit cell. Observe the reference atom X in the HCP unit cell. This atom will have 6 neighbors in its own plane. We also have an atom X connected to 3 more atoms in the same unit cell, as well as this atom X will be connected to 3 more atoms in the neighboring unit cell. We know that each corner atom touches each other atom in the HCP structure. Therefore, the distance between any 2 corner atoms is the atomic radius. Now, we have A is equal to 2R or R, that is, the atomic radius is equal to A upon 2. Let C be the height of the unit cell and A be the distance between 2 neighboring atoms. Consider the triangle ABO in the bottom layer of the HCP structure as shown in the figure. Here, A, B and O are the lattice points, and exactly above these at a perpendicular distance C by 2, the next layer atom lies at C. From the figure, in the triangle ABO, cos 30 degree is equal to AA dash divided by AB. Therefore, AA dash is equal to A root 3 divided by 2. But AX is equal to A divided by root 3. In the triangle AXC, AC square is equal to AX square plus CX square. Therefore, CX square is equal to 2 by 3 A square. But CX is equal to C by 2. Therefore, C by 2 the whole square is equal to 2 by 3 A square. Or C by A is equal to 1.633. To find the packing fraction of HCP structure, area of the base is equal to 6 times the area of the triangle ABO. Which is equal to 3 root 3 A square the whole divided by 2. Hence, the volume of the unit cell of the HCP structure is equal to the area of the base into C. Which is equal to 3 root 3 into A square into C the whole divided by 2. Considering the top layer, which has totally 7 atoms, each corner atom contributes 1 by 6 atom to the unit cell, and the center atom contributes 1 by 2 atom to the unit cell. Hence, the total contribution from the top layer to the unit cell is 1 by 6 into 6 plus 1 by 2 equal to 3 by 2 atoms. Similarly, the bottom layer also contributes the same 3 by 2 atoms. The central layer contributes 3 atoms fully because all the central layer atoms are well inside the unit cell. Therefore, the total number of atoms per unit cell is equal to 6. Packing fraction is equal to V by V, which is equal to 6 into 4 by 3 into pi r cube, the whole divided by 3 root 3 into A square C, the whole divided by 2. By substituting 2R is equal to A and C is equal to square root of 8 divided by 3 into A, we get packing fraction is equal to 0.74. Thus, the density of packing is 74% and hence it is a close packed structure. So, most of the metals crystallize in this structure. The given table shows the properties of some crystal structures with example. The properties consist of unit cell volume, number of atoms per unit cell, coordination number, nearest neighbor distance, and density of packing, etc. Both of them are close packed structures with coordination number of 12 and hence their packing densities are the same. Summary. Let us recap what we have learned in this module. The number of atoms per unit cell in HCP structure is equal to 6. A hexagonal close packing structure or HCP has 3 types of atoms, namely 12 corner atoms, 2 base-centered atoms, and 3 atoms in the middle layer between the top and bottom face of the hexagon. The height of the hexagonal unit cell to the distance between neighboring atoms, or the C by A ratio, is equal to root of 8 by 3, which is numerically equal to 1.6329. The HCP structure is a close packed structure with density of 74%. The coordination number of HCP structure is 12 and the atomic radius is equal to A by 2.